Did it? Okay, it should be recording now. It hasn't given me a warning yet. Oh, yeah. Oh, yeah. So here's where we were up to the end of the last workshop. We are going to just continue on the trilogy of classification, so to speak. Right? We talked about discriminative functions. We talked about the historic perception algorithm, and we're going to proceed to generative models, discriminative models, and hopefully that allows us to to have a better perspective. I would start by the warning that this class, in my view, is, this particular section, it may look like linear models and they are simple, but there is a fair number of technicality into it. So let's dive in. I don't know why this is not showing, but we're not covering Laplacian Bayesian logistic regression. Hopefully nobody misses that. So just as a reminder, we were talking to you about the modular view of supervised machine learning. And in this session and the next few, we're going to see more examples of essentially the definition of model and the different variants of doing this, and also choosing different objectives. We will not be able to talk about how to sort of optimize in detail most of this class, but the neural network section will give you a flavor about what finding the best W star or finding a good W star means. So let's remember we're talking about generative models, so we will be manipulating different probabilities. Let's start from a probability that we've seen many times. So the posterior distribution of the class, let's say class 1, we're doing a binary classification task. Say we're going to decide whether it's class 1 versus class 2. Then the posterior of class 1, due to Bayes' rule and the sum rule, is simply the data likelihood given class 1 times the prior of class 1, right? So this is likelihood times prior. Normalized the same term plus the counterpart in class 2, right? So now we're just going to do some simple manipulations. We are defining a new term by just taking the ratio of these these joint probabilities, right? The ratio of the likelihood times prior for the two classes, and take the log. Okay, no magic. We define a new term, and it's equivalent to basically the ratio of the joint between the data and the class label. Great. And then we basically put this term into the original equation. And we found something curious happened, right? So this big equation on top now translates to a simple expression of this A term, A of X, and the simple expression is called the logistic sigmoid function. What has happened is basically the multiple dependencies on both on the numerator and the denominator combined. So basically, this term only depends on the ratio of the two probabilities. Let's maybe do this for a sec. If we basically want to approximate the last term, we divide by the joint probability of X and C1 plus, and then this is basically the ratio of P of X of C2 over P X of C1, all right? And this term, according to the definition, is, this is basically X 1 over X A or X minus A, right? Right, okay. So Why is this manipulation worth talking about? First of all, um, it changes our focus from, or it gives us basically a different quantity that we can talk about and use, which is the probability ratio, log probability ratio A. And it shows that the quantity we care about, the class posterior, only depend on A as a quote-unquote simple function. Moreover, as we will encounter over and again, this logistic sigmoid function is very useful for classification, and this is the origin of it. There's no special trick. You just define a new quantity, and the posterior naturally comes out as a logistic sigmoid function. Right? What does this function look like? Right? So if we graph this, the x-axis is A, then the sigmoid of A is bounded between 0 and 1. It crosses the point 0.5 when A is 0, right? So recall that A is essentially log of P of x C1 over P of x C2. Then when the ratios are equal, the sigmoid function is the most uncertain, and when A is big, basically the joint of x and C1 is large, the sigmoid of A is approaching 1, and so on. So it's not just the sigmoid function itself is interesting, its inverse is also interesting. So if we just do the manipulation, it's easy to verify. I'm not going to do it here. By logging exponential to both sides, is that the logic function of sigma, now the function is called A because it's the inverse, right? It's basically log of sigma over 1 minus sigma. So because sigma is the posterior probability of class C1, 1 minus sigma is posterior probability of C2, essentially, then the inverse of logistic function is essentially the log of the ratio of the posteriors. Right, so that's interesting. The input to sigmoid is log of the joint probability between data and labels, and now we also have a quantity representing the ratio of log posteriors. And what this means is that the log of posteriors is 0 when the two classes are equally likely. And then when class C1 becomes dominant or very likely, the logic function goes up to infinity on the right-hand side. So that's interesting. So there's apparent symmetry for the sigmoid function that you can notice. Moreover, the derivative of the sigmoid function is a nice function as well. It's basically the sigmoid function times 1 minus itself. This is useful for speeding up calculations, such as for the gradient of the logistic regression or neural networks, as you will see. All right. So that's sort of a short interlude introducing the key quantities we will use. Now let's get to generative models, right? So in generative models, we're interested in estimating the class posterior probability through maybe the likelihood and priors that we can specify. So if we have multiple classes, basically C1, CK, we can define the quantity A sub k as not the ratio of data likelihood, but basically the log of data likelihood times class prior. Then we can essentially rewrite the posterior in the following way. It's basically a ratio of the exponential of this quantity A of k over the similar exponential of the similar quantities for all classes. That's the normalizer. So what this is called is usually, it's called a softmax function. Again, it's going to be very useful. Neural networks use it a lot because it is a smoothed version of the argmax function. What this means is that, so if basically if AK is the maximum, or K is the argmax of all A's, then exp of AK is going to be a lot greater than any AI for any I not in K. So this is due to the nature of the exponential function. It goes up very fast. So unlike AI and AK are really close, the posterior probability is going to be dominated by the largest log probability term, right? This slide from last year argues that, well, soft argmax might be an appropriate name, but nobody calls it soft argmax or very rarely. So this is colloquially known as the softmax function because it's not exactly, so P of CK is not exactly 1. It approaches 1 if the corresponding probability is dominant term, but and everything else is quite small, or it tend to be. So what it translates to in the, so if we draw K and then P of C little k given X, this will be a discrete bar graph, and it ideally should look like this. Basically, this is the argmax. K equals argmax of AK, right? Or AI. So, okay, so here's the mental picture for these log probabilities and their exponents. Now let's look at our first generative model for classification. We've been working with Gaussians a lot in the past 2 weeks. And Gaussians is one of the nicer distributions that arises in life. So let's just assume that class conditional distributions are Gaussians, right? We just write it out as follows. P of X given CK is some normalizer term and the exp of a quadratic term, X minus the mean of the K's class, times the inverse of the shared covariance matrix. It's the covariance is shared here simplifies a lot of things. And then basically every class has a mean, right? You may say, well, this model is a bit naive. Yes, it is, but let's see where it leads us. So remind ourselves that the A of X term is log of likelihood times priors, ratio of that. And we simply rewrite. So we know from a few slides ago that the posterior probability is nothing but sigma, the logistic sigmoid function of A, right? And the claim for this page is that if the class conditionals are Gaussians with shared covariance and separate means, then the A term is a linear function of X. Okay. Right. So this slide is sparse in words, but this is the tricky bit. So how do we see this? We do so by essentially plugging it in, right? We know the data likelihood is the term above, and we know that the A is done by taking the log of this. So A is essentially log of P of X given C1 minus log of P of X given C2 plus the log of the ratio of the two priors, which we leave, right? C2. Right. And if we look at the first term, this term is essentially some constant. The covariance shared, we don't care, plus log and x cancels out. It's basically the quadratic term in here, right? 1/2 x minus mu k, mu1 transpose sigma inverse times x minus mu1 again. And we have the similar term, but in the inverse, in the other sign, with the opposite sign for class 2. There's some other constant, well, actually the same constant, right? So if we look at these two terms together, we can see that the quadratic term of x cancels. Because in the worst case, the a term is the quadratic expression of x. Now the quadratic term cancels, and the linear term next to x in here is, so when we expand the quadratic expressions or the squares, there's a 2 times x, well, 2 mu1 times x that cancels out with the 1/2 there. So it's basically mu1, depending on which one we write it, we want x to be last. So mu1 transpose sigma inverse x. And the term downstairs is mu2 transpose sigma inverse x. And then if you combine these together, these are opposite signs, right? You get the expression below. So yeah, and sigma is symmetric, so sigma inverse and then sigma inverse transpose are the same matrix, right? Okay, so you can similarly verify the constant term W0. We're not going to do it here. So what just happened, right? So we just started with a Gaussian distribution and the logistic sigmoid term. And then we end up with a linear classifier. So that is pretty neat, right? So the Gaussian is exponentials of quadratic terms, and now the classifier is linear, right? Or the posterior probability is linear. We should be happy about that. And geometrically, this is what we just did. If we have two class condition, data likelihood class conditional Gaussians, they look like the red blob and the blue blob, and posterior probability is colored by the proportion of red ink on the right graph, right? So what we're seeing is a logistic sigmoid function here, right? So you ask, what we said 2 slides ago, that they have shared covariance is part of the model specification or assumption, right? So back to this picture, what we said is the model must have separate mean and shared covariance. Now, what we go back and say, what if we modify the model assumption or definition to say that if we allow sigma to be different for different classes, what will happen, right? So as we said, because it's Gaussians, you take the log, it becomes a quadratic expression. So quadratic is the worst or the most complex case we are dealing with. indeed it is. The book has this picture to show there are 3 Gaussians, 2 of them share a variance. The blue Gaussian has just that same variance rotating 90 degrees. And we can see that the discriminant function, or the class posterior, between the red and green one are linear, and the discriminant function against the blue one, where here the discriminant function means this contour line when the posterior probability is equal between the 2 classes, are quadratic curves, right? Okay. So what we have done is we did like what we call the model specification or definition, and then we looked at what discriminant function and what posterior probability we can get. And now we haven't the gap we want to fill here, as we'll do it again. The fundamental task is in machine learning is we have some pile of data, right? Like that sits in some database somewhere, right? And we want to recover the parameters of the model. And we have seen maximum likelihood estimates a number of times, so let's just do that again. So the function form of class conditional densities is conditional Gaussian. So if we look at the join of the data and the class label, it's basically the prior parameter we call basically PC1 as pi, and P of C2 therefore is 1 minus pi. And we can write out essentially the probability of observing the target variable, or the C's, give and the X's as follows. Basically, it's for each data point T sub n. So we have Tn and Xn here. That goes from n to 1 to big N. Then if the little tn is 0, is 1, actually, it's class 1, then the first term is active. If the little tn is 0, then the second term is active. Because all of these data points are assumed to be AID, we just multiply them all together. So this is the entire likelihood term, right? So what we do next is to apply the tricks we've exercised a few times to say if that term, just copied from the last slide on top, is the likelihood term, we would like to maximize the log of this likelihood term, right? So we just take the log. And now we try to solve for class prior, or pi, right? We can stare at this, right? So log of a long product of terms. Basically, there's one term for each data point. It's either the first bunch, or the class, the one corresponding to class 1, or the one corresponding to class 2. So there are n of these terms, so it's roughly like L of pi and mu1. L is a function of pi1, pi and mu1, mu2, and sigma, they are shared. It's basically a sum that goes from n to 1 to big N. And inside each sum, there is yeah, right. So there's class prior times the Gaussian term. So it's log of either pi, or I'm just going to write this loosely, plus log of some Gaussian term that we're not going to write, right? So if we're interested in solving for pi, then we only care about this front term. So let's do that. So if we take this, right? So the term here is pi raised to the power of Tn. So that translates to the first term. And then this in the second term, the log of the log term related to pi is 1 minus Tn times log of 1 minus pi. We just stare at them to verify there are still n terms being summed together, because when these two terms, only one of them is non-zero and Tn is either 0 or 1. So that's good. And if we're doing derivative of L with respect to pi, then what we need to do is to only take the derivative with respect to this term there. And we do so by looking at, right, so the summation sign remains, and Tn is data, it remains, and then log pi, the derivative of that is 1 over pi plus 1 minus Tn. Now we have 1 over 1 minus pi, and due to chain rule, there's a negative sign again. So we stare at it and say, if we set this to 0, what's the stationary point? So it's easier if we multiply pi times 1 minus pi on both sides. And the constant term that does not involve Tn gets, so this is Tn pi plus pi minus Tn pi. Did I miss a sign somewhere? Yes, I did, sorry. Should be a negative sign, and then these signs are flipped. Right, so the term related to Tn and pi cancels out here. So what we're looking at is basically this expression on the left. Sum over n Tn minus pi that's present in each of the terms is equal to 0. Therefore, the maximum likelihood estimate of pi is 1 over n summation of Tn. It also makes sense because this is the fraction of data points that has Tn equals to 1, right? Which is basically the number of the fraction of data points that is in class 1. Right. So it's nice to see that the solution, maximum likely solution to conditional Gaussians, is intuitive. So in the next page, or also in the book, there is a section that essentially covers or glosses over the estimation to mu and s, or s being the maximum likelihood estimate of sigma. So we can just stare at them to verify that they intuitively make sense. So the first mu1 is basically the mean of all points in class 1. And mu2 is the mean of all points in class 2. So that's intuitively making sense. And then since we said there is a shared covariance, we know that for the covariance estimate for class 1, for data points in class 1, is this expression 4.79. It's basically, it's not, again, the unbiased estimate, but it is the maximum likelihood estimate as we covered in week 1. And then the estimate for the overall covariance matrix is a weighted sum between the two of the covariances in class 1 and 2, which makes sense too. All right. Okay, so we have seen our first generative model for classification, what kind of decision boundaries it has, and how to estimate it, and what kind of, well, it happens to be linear, the discriminant, which is nice, or the posterior is linear in terms of the input x, which is nice, which is not a coincidence. We will see another function like this very soon. So now let's ask ourselves, what is the simplest generative model for classification where if the features are discrete, right? You can say that, well, if the feature lives in the real line, then Gaussians seem to be reasonable. But what if my features are categorical, like whether we're taking class remote or online, in which country people are currently located, and so on, right? These are all discrete variables. So also for simplicity, we know that we have already talked about that for class labels, we can encode them as binary or what's called one-hot encoding. So for discrete features, we can use the same logic to say that we primarily care about binary features, binary input, like 0 and 1. For non-binary, we can encode them as basically a vector of zeros with like one in between. So this might be, whether you're in China or you're in Australia, or maybe some people are dialing in from Malaysia, and so on. So also for a d-dimensional input space of binary features, so for now we're going to just assume that our input are all binary. We can expand them into different dimensions. A general distribution will be represented by a table of 2 to the power d entries, which is a lot. So we basically have input dimension right, input dimension 1, 2, all the way through d. And then we basically now assume this is our data table, right? Like this is data instance, data item, 1, 2, all the way to n. Then we can see that each of the positions can have an independent choice of being on and off, or 0 or 1. Let's write it as, so the data can be 1, 0, 1. So these are basically these slots that we can independently assign binary digits. So the total possibility is 2 to the d. So there's some normalization constraint of probabilities. So there's the degree of freedom slightly less, but not by much. So if we were to model this data vector p of x, given in here, we haven't even talked about class labels yet. So we can say class label, it's either one like Tn is either being 1 or 0. Right, if we're concerned about the join of p of x and class label, Tn, we can say that the input space is 2 to the power exponential in d, which is not very good. So what comes to the rescue is that, say, we simplify our model. Instead of modeling the world of all binary input of d dimensions, we're concerned with what's called a naive Bayes assumption, that given the class C, we assume that the features are independent of each other. So recall the probabilistic independence, conditional independence statement. It basically says the class likelihood or the data likelihood X given C is then a product of each of its dimensions, P of Xi given the corresponding label CK. Right? And assume we parameterize this because Xi is either 0 or 1. And we call the probability that the feature is on or being 1 as mu. Of feature I being 1 or is mu, then the data likelihood can be written out as, again, as a product of the parameters. Okay, we know we'd like to take logs, and products are handy. The reason we went through this slowly is that as you see that this basically the 0-1 encoding, the useful trick is to use basically x, 1 minus x, or t, 1 minus t as the exponent in the likelihood term, and that's handy for calculation. So assume we have the data likelihood as we wrote in the last page. Then what are the class posterior look like, right? So if we in here it's simple enough, so we're directly going to the multi-class case where A of k is log of the product of the likelihood and the class prior. We write out the expression, simplify it, which I'm not going to do here. We can find that the A of k is again a linear function of x and log of mu, which is nice. So what does this do, right? So a use case of naive Bayes classifier can be, say, spam classification, right? This is probably not for emails. And we assume email is represented as a list of tokens or words. This is probably not the best spam classifier, but it's a pretty good way to start. Then we essentially evaluate the probability, right? Mu k1 is, let's say, spam is 1, and then not spam is 0. Mu k1 is essentially the probability P, a probability of word k, right? If we go here in the spam class, right? The spam class. Then if you basically go through all the spam versus non-spam emails, count over the fraction of the word that appears in the spam, normalize it by the total word frequency, and then plug it into this log linear function. Then we're done. Right? Cool. So that's what we wanted to cover for probabilistic generative models. Another underlying theme that we are using here is for any a new model we want to cover, we want to talk about the simplest, because there's, as we said, Occam's razor. There is no good, if there's no good reason to use a more complex model, we should basically try and see if the simplest model might work or will fit. If there is a strong intuition by you, the data scientist or the machine learning researcher, where the simplest, the model assumption breaks, that's when we go to more complex model. For example, the naive Bayes assumption is quite clearly stated, and if your data obviously violates that, then that's the reason to use something else. what this class will also be giving you is essentially a vocabulary of simple models so that you can use on your real data as a good baselines, and also use to criticize or compare, articulate what exactly is different with the complex models. So, okay, moving on. Let's look at probabilistic discriminative models, right? The last session of the trilogy of classifiers. Don't know why this is the case. Right. In particular, we will cover logistic regression. So why do we want to use discriminative learning, right? So we want to learn to only discriminate between the classes in a lot of cases. In the motivating part of classification, we have seen that the class likelihood or joint data likelihood, some of the details don't really matter for discrimination. So why are we spending all the statistical effort to learn the details of data likelihood? If we're doing that, are we wasting essentially the available data we have and sacrificing for sort of a less accurate discriminant? This is also driven by the philosophy that if your goal in the beginning is to just sort your input into two classes, why do I care about what each class distribution look like, right? So why don't we just go directly for the goal? So what do we mean by learning a discriminative model is that we want to learn the posterior distribution of class given data directly. As we will see, typically this means fewer parameters to learn, very concretely for the Gaussian case. Right, and then as an added benefit, prediction may be better or may not. Right, so it's better when the class conditional density poorly approximates the true distributions, meaning that if the true distribution is too complex or learning of the data likelihood is inaccurate, then going for the discriminative learning posterior might be better. So again, there's no free lunch. If we're gaining more discriminative power, what are we losing, right? So the thing that we lost is for generative models, we could create synthetic data to validate our assumptions and to debug models, which are often quite useful. But for discriminative models, PX is not modeled, so we can't sample from the data. We will see more of that when we talk about sampling, graphical models, and all that. So the last statement on this page is basically a disclaimer that, sometimes, well, what we haven't said is about the convergence speed. It's like certain, So generative models sometimes can converge faster. Exactly which times, it's a lot deeper than we can cover in this class. But then it converges to a worse asymptotic classification performance. So we care about in this, if in the scenario of infinite data, how much better the classification can be. For each task, there's an inherent, essentially Bayes error that we cannot exceed. And right, so we can see that the speed going towards the classification error and the inherent error are other variables that we could consider in the theoretical analysis, right? So far we've been just working on X's because, talking about high-dimensional Gaussians is hard enough. Talking about high-dimensional Gaussians in kernel space is, or in basis function space is also hard. But now that we're in discriminative learning land, let's revisit basis functions. So what we are looking at now are surfaces of what's called Gaussian basis functions, basically concentric circles from a data point x, right? We can see now in the data space, this is the original space of the input, x1 and x2. The red and blue are the two classes, but they are not separable in the way. So let's say blue is C1 and red is C2, and we have C1 again here, right? So obviously they're not linearly separable. We've been talking about linear models, but if we use what's called Gaussian basis function or concentric circles, because there are only two basis functions here, like they're centered around somewhere in the red and somewhere in the blue respectively, and they have a fixed radius. If we project the data into this two-dimensional space, which is now defined by phi1 and phi2, we can say, oh, nice, now they are linearly separable, right? So this is the motivation for, and illustrates the power of linear models with basis functions, meaning that despite we're talking about linear models, we're not exactly talking about linearly separating the original input. In fact, if we allow arbitrary number of basis functions that are sufficiently good, then we can essentially separate any class that's separable. There's also a catch for that we will cover later. Right, so we can learn, in other words, we can learn nonlinear decision boundary in the original input space. And in here, the black curve transformed back to the original space is this circle here. So here's the catch, right? The top part of this slide basically just said what we just said. Classes are not linearly separable, and input can be linearly separated in a feature space. However, if classes overlap in the input space, then they will also overlap in the feature space. Like basically for the same value of x, right? So suppose we have a phi of a blue x, and around the same, in the same neighborhood, we also have a data point with the same value, but it's red, right? So it's the same input value, and the feature function of them are essentially equal. Therefore, the bad news is that nonlinear transformations cannot remove class overlap. It can only make it worse. To see that, well, like if for some basis functions, we can see that there exist x1 and x2, phi of x1 might be equal to phi of x2. For example, for Gaussian basis function, if x is sufficiently far away from the origin, then the kernel values are kind of similar. Okay, so keep this in mind. So what is the simplest discriminant model that we can learn? Remind ourselves, half an hour ago, we talked about conditional Gaussians, right? P of x given C1 is Gaussians, n of mu and sigma. Oh. Right. We're in that case, we saw that the discriminant function A is the linear function of x, right? So why don't we just use that conclusion and say, hey, that's a simple enough discrimination function. So let's just learn that. We just say now the class posterior is a linear function of the input basis vector transformed by sigmoid, right? sigmoid is called the logistic sigmoid function. So this whole thing is called logistic regression. This name is fairly misleading. It comes from statistics. So this is an example of essentially historically inherited names, right? You could think about the inside W transpose 5 as the regression part, and then you put the logistic function in front of it. But in machine learning lingo, the role of logistic regression model is to do classification. Okay. So again, we started with the conditional Gaussian generative model. So what's the difference? What changed? Where the functional form we're learning is exactly the same. We know how to absorb the constant term, so that we can just ignore that. So the difference is that we're now looking at linear number of parameters, which is W transpose, rather than quadratic, right? In the Gaussian case, we were looking at learning both W transpose, W0. Actually, take that back. We were learning mu1, mu2, and sigma and pi, and 1 minus pi is the same. Right, don't need to write that. So in the Gaussian case, we're learning these parameters. Moreover, mu1 and mu2 are linear in D. And sigma is quadratic in D. It's in effect, right, something like D times D plus 1 over 2, because it's symmetric, right? So when we say linear is in terms of input dimensions, of course, if we want a very expressive set of basis function, that input dimension might be big. And that's also exactly the case where we want the number of parameters to be small. And this W vector we're learning as a parameter is certainly linear in D, which is nice. Case in point, so logistic regression, I would argue, is a very robust model. I have, in my previous job in industry, and many of my colleagues have moved to industry, one of the Facebook models for news recommendation, that's more than 10 years ago, was a logistic regression model that essentially turns every item on Facebook as a feature. So there's billions of features, right? So with logistic regression, you can easily learn millions or billions of features. So for example, each person on Facebook is a feature, each news item you posted is a feature, so it's a giant, very sparse feature. And then the prediction is whether you will click or whether you will share the post. Okay, so that's basically our model specification. Moving on to our familiar pattern, how do you specify the model? Now we talk about how do we estimate the model. Again, maximum likelihood. So we have seen this now. Our data comes in as phi n and tn tuples, where tn is 0, 1, right? This is a classification task. As we have seen a few times by now, the likelihood of this kind of model with binary output is essentially yn raised to the power of tn times 1 minus yn raised to the 1 power of 1 minus tn. It's this acts as a selection, essentially, between two classes, where yn is this thing in the previous page. Right, so let's just write it out. Sigma times W transpose phi, right? so there's a number of terminologies as we have worked through likelihood functions, error functions, and so on, and we can see like the name, behind the different names they have a relationship. In here we want to minimize an error function which is a negative log likelihood, right? We want to maximize log likelihood, and these languages essentially mean the same thing. So we proceed by taking the negative log of the likelihood function we see upstairs, which trivially expands to essentially sum over all data points, tn times log of yn, y minus tn times log of 1 minus yn, right? So again, this is a very often used objective function. It's called the cross-entropy error function. The reason it's called cross-entropy is because of this something times the log probability of something is quite similar to the definition of information entropy that we haven't covered. So this is, I believe, chapter 1.6, if you want to read about it. Feel free to ask me as well, or one of the tutors to explain. So it's called cross entropy because the quantity that's being multiplied in front is different than the essentially posterior probability being taken a log of in the back. Okay, we still have a little bit of time, so let's cover how do we optimize this, right? So if we stare at this, right, so there is no analytical solution to this. And as we saw for a few rounds now, similarly for perceptron, what the general thinking for solving this is basically we have now an error function E of W. We want to find a stationary point, right? Take the gradient of E of W with respect to W, and if this is 0, then it is likely a local minimum. Right, so it's not a sufficient condition, as we will cover in the neural network section. But right, generally taking the gradient and then just keep updating W is a good idea. Basically, we update W in different rounds. W of the next round is W of the previous round plus some scale factor of the gradient. Okay, so we just rewrote the cross entropy term upstairs. That's nothing new. The next thing we do is that we basically expand the yn terms, right? So yn is sigmoid function of W transpose phi n. We just plugged it in, and plug it in both places. And now since we want to solve, like, find an expression for the gradient, we stare at this. The terms involving W is only inside the sigmoid, right? And sigmoid is like a function involving a little bit of terms and numerator and denominator and so on. So maybe we just pull out these two terms and then take their gradient with respect to W and then build it back up. So if we do it for the first term, we make use of the fact that the gradient of the sigmoid with respect to its whole input inside is the sigma function times 1 minus itself. So we do this. Now we have gradient with respect to W of the log of sigmoid. So what this translates to is, due to chain rule again, differential, like the gradient of the log of something is 1 over something, so we just write it And then we differentiate the sigmoid term with respect to W, then we just plug in the expression from the upper right-hand side. Oh, it's the sigmoid function of the same thing. We just copy it. And then y minus this thing, W transpose phi n. Okay. Now are we done with the chain rule? We're differentiating against W, so therefore there's a linear factor multiplying the W, which is phi n, so there's a phi n term. Okay, great. So we did this, we noticed that these two terms cancel out, we're left with this thing in the back. We'll deal with it later. So we do the same thing for the second term. 1 over 1 minus sigma W transpose phi n. All right, now we have differential with respect to the thing inside. The term 1 has a gradient of 0 because it's constant, and then the second term, it's basically then negative. Right, so if we differentiate the second term with respect to W, then it's going back to what we just did upstairs, but with a negative sign. So let's do that. Just record that. Phi n 1 minus sigma W transpose phi n. Okay, we just don't need to do extra work. Right, phi n. We are done. So now what has happened? The three terms multiply with each other, so we can see this one still cancels out. And this second derivative simplifies to minus sigma W transpose phi n times phi. All right. Now we put it back into the gradient of E. So we, for example, plug in this term back in here, right? And we just keep copying the summation part, Tn 1 minus sigma W transpose phi n times phi n plus 1 minus Tn Okay, you might say, oh, are these vectors or numbers? You're just writing them as numbers. What's happening here is basically these terms, they are scalars. And then a scalar times a vector is a vector, and the gradient of a wave vector should be a vector, so we're okay. Now, what does that do for us? We just expand it and then stare at it again. Tn minus Tn sigma W transpose n plus minus here minus 1. The term sigma W transpose phi n, and then plus Tn W transpose phi n times phi n. All right, I believe we're done expanding. So notice that this one and that one cancels out. What we're left with is basically sum over each data point, the term involving Tn, and also the term involving the sigmoid function times phi n. So we notice that this is the definition of yn. I missed the term, apologies. So this should have a Tn multiplied by phi n. So what it has is basically, and we flip this negative sign, like merge the negative sign inside. Okay, now this is simple. What just happened? And why are we doing this? So the reason is as follows. I hope you will find this term familiar. Right, so what we just did is basically the, yeah, and if we're doing stochastic gradient, right, so if E of n of w, then it's basically yn minus Tn times phi n. This should look familiar because it's exactly the same update rule as, or almost the same as perceptron, right? In the perceptron, if the label disagrees with the ground truth, then we essentially add or subtract the input. And this is essentially what's happening here too, except the output coding is a bit different, but that means the front term is either 0 or 1. So this is nice. Familiar, yeah, picture comes back again. Okay, so I feel the simplicity at the end and the connection to perceptron is worth covering for logistic regression because it also connects to very closely to what we are about to talk about in the next 20 minutes, neural networks, or we will actually talk about that on Friday when we get to talk about backprop. So what this says is if there is an error in the network output with respect to the ground truth, then update the weights based on the feature value. So that's nice. So we can see that the different learning or machine learning models and algorithms are not only connected at the modeling level, but they are also connected in the algorithm level, right? And logistic regression, as I said, is quite robust. And it's often like your go-to baseline. So much so that a number of machine learning class colleagues and I used to joke that here is the master algorithm for machine learning. If you're given a task, what you do is you represent your labels, you extract features, and then you try logistic regression. Right? If it works, then you're done. Works well enough. It's basically, it gives you an intuitive sense of how difficult the problem is out of the box. And it's also quite easy to understand, like because there's only one set of linear weights. But on the other hand, you should be very careful if you're trying to interpret the weights though, because the weights does not equal feature importance in linear models. And it's quite tolerant on mutually sort of dependent and redundant features. Basically, some of the features will get some weight, and then some of the features will not get much weight. And so despite we covered the gradient descent algorithm, we also can't find a global optimum, so we're just finding some good sets of weights, right? If the logistic regression fails, then we design fancy algorithm to tackle your problem. Or better still, reduce your problem, transform your problem so that we can try logistic regression again, such as put inputs through basis functions and so on. So of course, these are practical. This is for mostly practices or applications of machine learning. We didn't discuss like how you optimize and do inference, and we didn't say anything about asymptotic bounds or theoretical guarantees or what your evaluation setting is. You should take all of that into account, all right? So this is basically the classification chapter. We talked about what are the classifications problems, what a little bit about decision theory, and then basically the trilogy of ways of building a classifier: discriminant functions, generative models, and discriminative models. Along the line, what I personally like is that we cover the origin of the famous logistic function, and then we cover the logistic regression in a way that it connects nicely back to the old, but still very insightful perceptual algorithm. All right, so I'm going to pause for some questions if there's any, and then we're going to start the neural network part. Okay, maybe there's no question. People all understand this, which is great. So let's, again, with the neural network section, we're going to define what neural network is, or basically specify the models. And then we're going to look at the training part, basically involves the objective function and how to optimize it. We will talk about what the famous error backpropagation algorithm, and then we will briefly talk about how you implement it in modern software and hardware computing stack, basically by automatic differentiation, which is cool. And we talk about a very small sample of tricks on how to regularize neural networks. So that will be our plan for today and Friday. Before that, since we will be talking about optimization a little bit, a primer for this time is convex functions. What are convex functions? Some of you may have encountered it. Some of you have not. So this 1 minute preliminary is mainly for those who have not, or if you have encountered it but forgot. So a convex function, f of x, here on the one-dimensional x, is one which every chord, basically, if we connect any two lines on the function, it sits above the function itself, such as this one, and such as we can draw one here too. So they all sit above the red curve, the function itself. Mathematically speaking, this corresponds to basically the function. What does it mean by essentially sitting above the line, right? So if we take any point between the point A and B, the value of the point can be expressed by a linear combination of the two ends, with lambda being in between 0 and 1, right? And the function value of this point, x lambda, is less or equal to the linear combination of the function at the two ends with the same weight, lambda. So this is the expression of basically a convex function, right? An equivalent definition is that the second derivative of f is always non-negative, right? How do you see that, right? The first derivative of a function is basically, okay, let me use a different color. So the first derivative is basically the tangent lines of the function, right? So these are f primes, like let's say this is f prime at point B, and this could be f prime at point A, pardon the drawing. And then this is essentially f prime at x lambda, right? The second derivative is the rate of the change of these tangents. So we can see that the rate of change is negative at point A, and it's positive at point B, and in between it continuously increases. So therefore, the rate of change for the tangents of the function is positive, or non-negative. So these functions are nice. They look like essentially a high-dimensional ball. If we want to get to the bottom of the ball, we just start from any point and then slide, right? Imagine ourselves being infinitesimally small, and we can just follow the negative of the gradient or follow the gravity, so to speak, and slide. And you can think of many of these functions when we work with them, such as x squared or quadratic functions are nice. X times log of x, so it's a relative of the cross of entropy function we were looking at. That's nice. And x transpose times some positive semi-definite matrix times x itself. So we have also seen this quite a bit in Gaussians and so on. So note that the intuition for convex functions also holds in high dimensions, right? What's also nice is this leads to an often used Jensen's inequality if we want to derive new machine learning objectives and inference procedures. Basically, it's a generalization of 1.114 above for more than like 2 points A and B. So the function value of an average, like basically, so this is an average. Well, we can think of it as average x. So this is less than the average of the function value, right? So yeah, right. So here is the definition of feed-forward neural networks. So we can pack convex function for a bit, and then we'll invoke it when we're talking about optimization. There are two key ideas, essentially, from logistic regression, right? So we can see there is kind of a continuum between logistic regression to neural networks. So we generalize linear models with activation functions. So generally linear models, W transpose phi. Now, in logistic regression, we put this logistic sigmoid as an activation function. In here, we are considering a larger class of activation functions, right? And then the second key idea, a lot of you guys are computer scientists. Some of you are not. You're in science or stats and so on. For the CS person, recursion should be a familiar concept, right? So what prevents us of shoving the output of one layer of logistic regression to another layer, well, or what's called layer with another set of weights? So this is exactly what's happening. So equation 5.1 is basically a rewrite of logistic regression with a generic activation function f. Equation 5.9 here is essentially doing it again. So this is the expression above, except now we call FHs. And then we just pass it through another set of weights. Another thing is that we can have multiple logistic regressions or similar models working in parallel, right? So we have multiple of these first layer linear combinations passing through an activation function, and then we put them through another set of weights. So if you think 5.9 is a bit hard to visualize or analyze, conceptualize, here's the picture, right? Figure 5.2, from the input x, each z is essentially h times some weight vector transpose x as a vector. And then there are three intermediate nodes, z. Each of the y's are essentially sigma of some other weight vector, and the second layer transpose z. Okay, I'll label this as first layer weights. So this is this picture basically summarizes the recursive composition. So this structure, as you can see, is very general, right? It does not prescribe the network or between each x and each z, there has to be a connection, or there is none. For example, this one could have a connection, but it doesn't. This one could have a connection, it doesn't. It can have skip connections. The connections can be sparse. One main constraint is that we would require feed-forward structures. We don't want loops. So the direction of information flow is this green arrow. Why is that? It's because we would want yk, the k's output, to be a deterministic function of x where we can just compute. If there are loops, y depends on z, z depends on x, and then z depends on y again, then we don't know what value of y takes. That's bad, right? So you can see that as this computational graph or structure becomes more complex, we need some conventions to avoid confusing ourselves. If we refer to the number of nodes that here are denoted as cycles, there are 3 different nodes, x, z, and y. But if we look at the number of weights that are the learnable parameters for this model, then there are 2, right? So basically weights of layer 1 and then layer 2. So the number of layers in terms of terminology, at least for this book, refer to the number of weights rather than nodes. Right? You might say, oh, why do we take the trouble? Right? So here's the reason. Right? In logistic regression, right, okay. If we learn y as this, then we are still essentially looking at linear function of basis functions, and the basis functions are fixed. Right. So that might have limitations. We want flexible models. Ideally, we want models that can approximate any discriminative function, right? And neural network does give us such a guarantee. In fact, these guarantees were proved in the late 80s. So basically, not, and the proof is nice. It states that a 2-layer network can already gives us a guarantee. Basically, the network we saw on the previous page, if we desire any input-output mapping in a continuous space, as long as we're allowed to have an arbitrarily not large number of hidden nodes, z's, we can approximate that function. That's what it says. So this formal statement says a 2-layer network with linear output can uniformly approximate any continuous function on a compact input domain to arbitrary accuracy. So actually, uniformly approximate to arbitrary accuracy is a technical term. You don't need to care about this too much. So if the network has sufficiently large number of hidden units. Moreover, it says, it basically says we only need 1 layer of nonlinearity. So what it says is the output can be linear output, but the hidden unit can have a nonlinearity. Then the combination can essentially approximate arbitrary functions. So to make the point, the book has an illustrative example, right? So the target function is quadratic sinusoid, some triangle, and a step function, which is sort of has a sudden change, right? And what it does is the perceptron here is well, it's only a 2-layer network having only 3 hidden units with 10H activation. So 10H is a shifted version of sigmoid to make it an odd function. It says with 3 hidden units, we can already approximate all of these functions. Moreover, it shows the hidden units, the output of the hidden unit are shown by the 3 dash curves. Basically, if the 3 dash curves are learning these, then their linear combination can learn the target function, which is quite amazing. It's interesting that, for example, in the last case, where we aim to learn the sine step function, right? But one of these hidden unit functions, it learns actually the sine flipped step function, right? So how does this help? That's because if we just make the weights of the last layer negative, you will approximate the step function as well. We'll get back to that in a minute. Okay, we're almost at time. Comparing to perceptron, I'm just going to talk about one more thing and then we wrap for today. So a neural network, you can arguably think that it behaves like a multi-layer perceptron, except perceptron restricts itself to the step function, right? Once we relax that assumption, and allow many other activation functions, neural network does have these universal approximation properties that are very nice. So that's the reason that they are smooth and differentiable is because, okay, we want to compute gradients. Like we did for and we want to find a good set of weights. Right, so here are 2 questions to ponder about for the model. If all activation functions are linear, then it does not have the universal approximation property, so it's equivalent to a essentially 1-layer linear network. Because the linear combination of linear combinations is linear. If the number of hidden units is smaller than the number of input dimensions, we talked about arbitrarily not large number of hidden units, and they're quite powerful. If we restrict the number of hidden units, then this amounts to dimensionality reduction. Basically, we're reducing information rather than making the input richer. So we'll see more of that around PCA next week, right? So yeah, I think we'll wrap here today and then continue the rest of neural networks tomorrow on Friday. Is there any questions? I'll stop the recording.